We are here to discuss, the first lesson in Module 3. This is the first time this semester that you will not see any R in this lesson. The R is coming in this module, but we really want to get some mathematical framework that's fundamental to this course, fundamental to what we will be doing as we move forward. So what we want to discuss is really an introduction to random variables and an introduction to probability. In particular, we will discuss probability mass functions and probability density functions. Well, in probability and statistics, we consider experiments for which outcomes cannot be predicted with certainty, and these are called random experiments. We can, however, describe every possible outcome, and the set of all possible outcomes is called the sample space. It's denoted S. Now, if A is any subset of the sample space, we call A an event. So far, we have defined the words sample space and event, two important words in probability. Well, as a remark, an event can be a single outcome or a collection of outcomes. It's just some subset of the sample space. Now, here's an experiment where we can think about this language. Let's take a standard six-sided die and roll it. The outcome, or an outcome, would be the number of dots facing up when you look at the die. So our sample space, which consists of all outcomes, well, it's six-sided. So the possibilities are, we see a 1, we see a 2, we see a 3, we see a 4, we see a 5, or we see a 6. 6 total outcomes in our sample space. Now, just to get the language of events, some possible events, maybe A is the event that the die lands on a 2. Well, A is a subset of this. A would just be the set containing the element 2. Another possible event, B, could be the event that the die lands on an odd number. In this case, B consists of 1, 3, and 5. Those are the odd numbers between 1 and 6. C could be the event that a die lands on a 5 or a 6. So C would be 5, 6, this set. And finally, suppose D is the event that the die does not land on a 4. Well, then D is the set containing 1, 2, 3, 5, and 6. Those are just some examples. We assign probabilities to events. So in this example, suppose the die is fair. That means all 6 faces have an equal chance or probability of landing up. How could we figure out the probability of each of these 4 events? Well, we can count here. So you notice that we have 6 total outcomes. So there are 6 total outcomes. This is the number of elements or cardinality of my sample space S. And then event A, well, there's only one outcome here. And so the probability that this event occurs is 1 over 6. For event B, you notice B has 3 outcomes. Another way to say that is the cardinality of B is 3. So to get the probability that event B occurs, well, we would just take 3 and then divide it by the cardinality of the sample space, 3 over 6, which is 1/2. Now, similarly, if you want to talk about the probability of C occurring, C has 2 outcomes. So we would get 2 over 6, or 1/3. And then finally for D, you notice D has 5 outcomes. Cardinality of D is 5. So the probability of D, 5 over 6. Maybe I will underline all of these. Now, the language we have seen, a sample space is a set whose subsets are the events. So just to review some basic set operations, I'm going to shade some Venn diagrams. Here I have my sample space S, and then I have these two events A and B. What's the union? And this is the symbol here. The union is everything in A together with everything in B. We took all, so far I have all elements of A, and I add to this all elements of B right here. This is my union. Next one, the intersection. Intersection, you must be in A and in B. So that would only be here. These are the elements in both A and B. Union is an or, intersection is an and. We talked about these in the first module. Now, complement. This is all elements not in A. So I would shade everything except what is in A. Wonderful. Now, here is random variables. This is one of the main ideas in this lesson. In order to model outcomes of a random experiment, we use random variables. So what is a random variable? Well, a random variable assigns a numeric value to each outcome. Numeric is the important word here. There are advantages mathematically to working with quantitative information. Now, as a remark, this is really a mark on notation. Often capital letters, such as, say, capital X, capital Y, capital Z, like this, denote the random variable. Denote the random variable, while the corresponding lowercase letters this would be, for example, little x, little y, and little z. These are values of the variable. As an example, let's suppose we select a position on a DNA sequence at random and consider the type of nucleotide residue. And suppose, moreover, we are given that 30% are adenine. This we use an A. 30% are thymine. This we use T. 20% are cytosine, C. And 20% are guanine, G. Well, we can define a random variable Y so that outcome A has value 1, T has value 2, C has value 3, and G has value 4. Then, if you wanted to think about probabilities with the information we are given in the problem, the probability that capital Y is 1, well, this equals 0.3. The probability that capital Y equals 2, well, this is also 0.3. The probability that capital Y is 3 is 0.2. And finally, the probability that capital Y is 4 is 0.2. So this is just an example with a random variable and probabilities. But I want to use this and move into some language and discussion. A random variable X is discrete provided, well, either there are a finite number of values of X. This is what we just saw in the last example. We have 1, 2, 3, 4 possible values of random variable Y. This is a discrete random variable. Now, this was an either, so, or there are countably infinite number of values. You really want to think, well, you could list them all, for instance. So what's countably infinite? For example, the set 1, 2, 3, 4, 5, keep going forever. This is positive integers is countably infinite. So some examples of discrete random variables. We just saw one on the last page, but another one would be the number of students enrolled in a math class at Northeastern University, or the number of Gs in some nucleotide sequence. These are two examples of discrete random variables. Now, the other type of random variable is a continuous random variable. A random variable is continuous provided, well, it can assume any value, and usually in a defined interval, or maybe a collection of intervals. But I will just leave it like this, in a defined interval. And quite often, measurements that we take are modeled with continuous random variables. And two examples, the height of a tree in feet, or the weight of a lightweight mailboxer in pounds. Now, this is a very important slide. It's very important that we understand the difference here. You notice I have made these stars in magenta. So we have functions in probability that we will use a lot. Every random variable has an associated probability distribution function and cumulative distribution function. But how we go about calculating these, especially the probability distribution function, fundamentally different for a discrete random variable and continuous random variable. So let us begin maybe with the easier one, which is a discrete random variable. So in this world of discrete random variables, think the values your random variable can take are a finite set, or maybe something like the integers. Okay, we have what is called a probability mass function. And it's quite simple to define. F of x, it gives you the probability that your random variable takes on value x. So this first one is capital X. Oh goodness. The first one is a big capital X, and the second one is little x. All right, this is what it is. Now we've seen the probability mass function already. If we back up 2 pages, here's our very first probability mass function. You see, we have the probability of each outcome. Very nice. Well, in the discrete world, if you want to calculate a probability of a range of values occurring, we will be adding here. So, for example, here's an example. Let's take the tossing a fair die. Then f of x is 1/6 for x equals 1, 2, 3, 4, 5, and 6. Right? In fact, this is very similar to the first thing we talked about. If you have a fair die, all sides are equally likely. Each will have probability 1/6 of appearing up. Okay, so if you wanted the probability, say that 2 is less than or equal to capital X is less than or equal to 5. Well, to calculate a probability over a range of values, we add. So this would be a sum from x equals 2 to 5 of f of x. And in this case, we just have 1/6 plus 1/6, 2, 3, 4, and 5, which is 4/6 or 2/3. Okay. What I wanted to illustrate, though, was that when you have a discrete random variable, if you want to calculate the probability over a range of values, we add. This is very important. Now, continuous random variables is very different. Probabilities do not come from adding up a collection of finite numbers. In fact, your continuous random variable is defined over an interval of values. So maybe I'll put stars here. In this world, I'll put it above. In this world of continuous random variables, probabilities are areas. Fundamentally different. Over here, we add things up. Over here, probabilities are areas. So we do not have a probability mass function. In the continuous world, we have what's called a probability density function. Now, I cannot say that little f of x is the probability, capital X equals X. That is not the case in the continuous world. But I mentioned probabilities are areas. So in the continuous world, what is true is if you want the probability that A is less than or equal to capital X is less than or equal to B, you see we calculated one of those in the discrete world over here. We just added. But in this case, it's going to be an area. Well, let's draw a picture, and then I'll write down what it is. Okay, so we have an A, we have a B. I'm not sure what my function is, but let's say this is my probability density function here. Say this is f of x. Then the probability, well, it's area. So it would be this area here under the curve and above the x-axis. This area is what gives you probability. Now, what is this area? Well, we know from calculus, say it's an integral, a to b of little f of x dx. So this is fundamental to our understanding of probability, is the difference between a discrete random variable where probabilities are sums and a continuous random variable where probabilities are areas, or another way to say that, it's a definite integral. All right, we've done a few examples of a discrete random variable. Let's do one where we look at a continuous random variable, but let me put stars around this. Very, very important. Okay. As an example, and this is what I mentioned when I introduced continuous random variables, but let's suppose X is the weight of a lightweight male boxer in pounds. And the rules of boxing say that this weight is between 130 and 135 pounds. So we take possible values, or we see the possible values of this random variable. Well, it's this closed interval from 130 to 135. Let's assume the weight is equally likely to fall in this interval. So then the PDF, probability density function, is 1/5. Let's draw a picture. So say here's 130 and here's 135. And then my function value is up here at 1/5. Okay, here's a graph of this probability density function. Now, we have two questions. We want first the probability that the boxer weighs between 131 and 133 pounds, and then the probability that the boxer weighs exactly 132 pounds. Okay, well, we answer this question using area. here. So for part A, what we want is a probability that 131 is less than or equal to x is less than or equal to 133. And well, you could write this as an integral from 131 to 133 of 1 over 5 dx. But let's just do this using area. We can use geometry here. So if we have 1, 2, 3, 4, and there's 5, what we want is this area. We go from 131 to 133. Well, this is just the area of a rectangle. So we would have here, this is 2. Maybe I'll do this here. The height is 1 over 5, and this is 2. So to get this, you could integrate. You could also just multiply the area of a rectangle. 2 times 1 over 5. The answer is 2 over 5. Next one, find the probability. Well, this is a really great question to think about. Probability, the male boxer weighs exactly 132 pounds. So we want the probability, capital X, equals 132 pounds. First of all, it's very important to understand in the continuous random variable world, probabilities are areas. So what you're asking yourself, here's 132. You're asking yourself for the area under the curve just sitting over 1 point. Well, it's two-dimensional area. Well, this is 0. Another way to think about this, what would this be? If you integrate from 132 to 132 of anything, you just get 0. Well, maybe I will say this as a note. I think about it in terms of areas, but it is also the case, properties of the definite integral, that if you have the upper and lower limit the same, this integral is 0. And this is important here. So I'm going to even write this. So this is a remark I'll put down here. Anytime x is continuous, maybe I'll even call it y, if this is a continuous random variable, then the probability that capital Y equals any given value is always 0. And this is, well, I mentioned continuous random variables, discrete random variables, fundamentally different. And this is one way we see immediately the probability of a continuous random variable being exactly any one value is 0, really, because probabilities come from areas. Let's do one more example, and then I will just briefly mention cumulative distribution functions. We will really see these more in future lessons. So here, I'm supposing we have 2 random variables. One is random variable x, one is random variable y. Well, you can see, because I use the word mass and density, that x is discrete and y is continuous, but how could you tell if I didn't say that? Well, you notice that x takes on these finite values. X is definitely a discrete random variable. Moreover, y has values that occur in this interval. Y is a continuous random variable. Okay, well, the functions given, they look similar. F1 and F2, the formulas look similar, but how we calculate the probabilities is very different. So let's calculate the probability x is bigger than 2 and the probability that y is bigger than 2. Okay, first, well, for x, the probability that x is bigger than 2, you see, I would just add over the values here that are bigger than 2. In particular, this is f1 of 3 plus f1 of 4. Now, we see this is 3 over 8 plus 4 over 8. We get 7 over 8, which, as a decimal, this is 0.875. All right. Next one. Well, y, this is continuous. So if we want the probability that y is bigger than 2, this is area. Technically, we would integrate. So y ranges from 0 to 4. We would integrate from 2 to 4 of y over 8 dy. Now, let's just, we could integrate this. It's just y over 8. We could ask R to do this, and we will do more of that in the next lesson. But I'm really focused on area in this lesson. So let's look at a graph of this. Here's the graph of this probability density function. Now, what am I wanting here? Well, I want the area, this area from 2 to 4. We could calculate this geometrically. So one way we could do this, you could take the area of the entire triangle and subtract off the area of the white triangle. Maybe I will do it this way. So the area of the entire triangle would be, well, the base is 4, the height is 1/2, and then we have 1/2, base times height. This is 1 as it should be, that kind of thing, properties of a probability density function or probability mass function. We will get into those in the very next lesson. But for now, I just calculated the area of this larger triangle and then subtract off the area of the smaller one. And this has area base times height. Well, that would be 2 over 8, which is 1/4, and then times 1/2. So altogether, we have 1 minus 1/4. This is 3/4, or if you want the decimal, we have 0.75. Lovely. Now, as I mentioned, I'm only going to briefly discuss cumulative distribution functions because we're going to do this much more. So every random variable has a cumulative distribution function. In fact, it's really defined the same. You take the probability, so capital F of x is the probability that the random variable is less than or equal to little x. So in the discrete world, it's a sum. This is really what I just want to mention here. Capital F of x, we would add overall, say y less than or equal to little x. We add up f of y. In the continuous world, well, you have some f of x, probability density function, and you have some value x. Now, to get the probability that capital X is less than or equal to this little x, you see it's this area all the way up to x. So this is an integral. So we would have capital F of x. This would be an integral. Well, I don't know what my values are, so I will just write it as, say, minus infinity to little x of, say, f of t dt. Now, we will do more of this, but the real thing to think about is area. So it's all the area under the curve up to little x. Okay, this is the end of our first sort of introductory lesson on random variables, and thank you so much.